Hello, today we are going to be talking about Wi-Fi. So, what is Wi-Fi? Wi-Fi is actually an invisible bridge that plays a very important role in the journey of our day-to-day information. It utilizes techniques like OFDM and QAM to face the challenges of physical connectivity, meaning in the early days, there were a lot of messy wires required to be actually connected and debugged to actually establish a good physical connection. But Wi-Fi have solved that, and it's actually now transforming a lot of industries from education to healthcare to robotics.
This slide shows the evolution of Wi-Fi technology, which is an ongoing effort to improve data rates, battery efficiency, and communication rates. So, in the early foundation between 1987 and 1999, the first IEEE 802.11 standard supported a very low speed of only 2 megabytes per second. This was followed by 802.1b, which operated in the 2.4 GHz band and increased the speed to 11 megabytes per second, making Wi-Fi commercially viable. So at the same time, 802.11a was introduced in the 5 GHz band using OFDM technology to achieve speed up to 54 megabytes per second. So next, we go to OFDM era from 2003 to 2009. So the 802.11g standard combined the good propagation of 2.4 GHz with higher data rates. So a major breakthrough comes with 802.11n, also known as Wi-Fi 4, which introduced MIMO antennas. So this significantly increased data rates, reaching up to 600 megabytes per second. So next we go to the modern gigabyte Wi-Fi era from 2013 to the present, 2026. So 802.11ac or Wi-Fi 5 further improved performance by using wider channel bandwidth and higher order modulation such as 256 QAM. So this advancement allow Wi-Fi to support high user density environment and modern data intensive application. And overall, Wi-Fi has evolved from basic wireless connectivity to the high-speed, efficient communication system used worldwide. Next, I will talk about the impact of Wi-Fi on society, industry, and also in science. So first, in society, Wi-Fi has become a basic necessity in our daily life. It enables remote work and also online learning, especially during the pandemic. People can attend class, meeting, and training session from anywhere. Wi-Fi also support multiple devices such as smartphone, laptop, tablet, and it powers our streaming, online gaming, and digital entertainment, which are now a part of our modern lifestyle. And in addition, Wi-Fi improves access to e-service such as online banking, e-government service, and digital platform, making the service faster and more convenient for users. Like right now, we use QR to pay and we need to connect Wi-Fi. So it's make our daily life easier using this. And then the impact on industry. So from the industry perspective, Wi-Fi plays a very important role in automation. So it supports real-time monitoring, control in industry, enabling the smart factories, logistics system, and smart building. Wi-Fi is also widely used in IoT application where devices communicate with each other wirelessly. And one of the major advantages using Wi-Fi is low cost, scalable, and easy to deploy, which makes it suitable for both small and large-scale industry. And in terms of science and research, Wi-Fi have advanced wireless communication system. It enables the use of technologies such as ODFM or OFDM, MIMO, and high-order QAM. So researchers can study signal behavior in noisy and multipath environment through the simulation and VR analysis. And this concept can be linked to real-world performance. Next, we go to challenge and opportunity. So despite its advantages, Wi-Fi also faces several challenges. So one of the major challenge is battery congestion, actually in the 2.4 GHz and 5 GHz band. And in that environment like house and city, interference can reduce the performance. And Wi-Fi performance can also degrade due to multiple fading and physical obstacle. And high order modulation is sensitive to noise, although it's fast. And there are also security risks caused by weak configuration, which is password, and outdated service. on the other hand, there are also opportunities for the Wi-Fi. So, artificial intelligence can be used to manage network traffic and reduce interference. And advanced signal processing technique like beamforming and error correction can improve reliability, especially in crowded area. Wi-Fi could also be integrated with other networks to provide seamless connectivity. So with faster speed, Wi-Fi will enable the smarter home, smarter industry, and smarter cities in the future. So continuous innovation can make the Wi-Fi safer, smarter, and more efficient in the future. Lastly, future outlook of Wi-Fi. So Wi-Fi will become faster and more reliable with new standards such as Wi-Fi 7. Lower latency will improve the video call, online gaming, and also real-time application, which is like lower delay. Wi-Fi will also work seamlessly with the 5G and 6G network, allowing smooth switching between the connection. And future network will be able to adapt automatically to changing condition using the smart technology. And most importantly, Wi-Fi will support emerging technologies such as virtual reality (VR) and smart automation, shaping the future communication and smart living.
Hello everyone, I am Basil. I'm going to be conducting the Wi-Fi simulation, which is essentially an OFDM simulation. OFDM is just an acronym for orthogonal frequency division multiplexing. Complicated name, but we'll get into that later. Firstly, we have to understand quadratic amplitude modulation. It's a fancy name, but we can break it down easily. Quadratic, the Q in QM is actually just a simple expression that means we have two signals, two sinusoidal signals that are shifted together by 90 degrees. That's just the Q. Or as for the QAM, it's just the summation of those two signals together. Depending on that summation, we can get an output out of the QAM system that is very discrete. For example, if we have 16 QAM, we have 16 distinct values on the constellation diagram. The constellation diagram itself is just an expression uh, of the output signal, which is, as we discussed, the summation of those two first signals that are shifted together by 90 degrees. Meaning, meaning a constellation diagram has two axes. The x-axis represents the amplitude of the first signal, and the y-axis represents the amplitude of the other signal. And when I say the other signal, I mean a signal that is shifted by 90 degrees from the first one. Now look at the output of the 16 QAM. It will have 16 different values. Each value, meaning each red dot, will represent a specific amplitude and phase of the output signal. The inner dots represents a smaller amplitude, and the outer dots and the outer dots specify a higher amplitude of the output of the QAM system. To demonstrate the QAM system, we will make a simple simulation using MATLAB and Simulink. The simulation was conducted in two parts. The first part is the Simulink block diagram using a simple two-block system. All the other blocks are just to display the results, but we have the random integer generator and the QAM system. All the other blocks are just for display, especially the outer blocks that these are used just to make the script for the simulation. We will now see how the simulation is done. After we run the Simulink, we use the variables extracted from it to run the script of the animation The animation will output two different diagrams. One is just to show the integer being sent, and the other one is showing the corresponding constellation diagram output. As you can see, each number has a distinct point corresponding to it on the constellation diagram. See 13, 14, 2, very distinct numbers representing each integer. This is the sample of the code that I used to get the actual animation. The most important outcome is that the receiver only needs to know the constellation diagram point, meaning that the receiver will only need the specific phase and amplitude of the signal being received. This is a very important thing to note. Okay, now as we discussed in the first part, the output of the QAM is actually just an amplitude and phase of signals that represent a symbol. Now, here's the problem that the OFDM is trying to solve, or one of the problems it's trying to solve is, what if we wanted to send, say, 52 symbols together? This is what the OFDM is capable of. Okay, now this is the setup for the OFDM simulation. Look at the integer and the random integer generator. It actually generates 52 numbers at once. And 16 QAM system actually takes those 52 symbols and outputs 52 different constellation points. Those constellation points can actually be the same point, just repeated. That's okay. Just like we are sending, say, I want to send the same number twice. That's also possible. We take those symbols coming out of the QIM and we input them into the OFDM modulator and then the channel and then the demodulator. This is all the simulation is all about. See, we have a modulator, channel, and demodulator. Okay, now let's run the simulation together. Uh, the simulation will have multiple outputs, well, two of which are constellation diagram of the transmitter and constellation diagram of the receiver. And then we have the spectrum of the signal that's actually being transmitted. Okay, when we say a spectrum of the signal, we just mean to assign the amplitude to each frequency that is being transmitted. That is just what it means to have the frequency spectrum. And as we can see here in the frequency spectrum, which we will later show, uh, there are a lot of signals being transmitted at once at different frequencies. This is the actual process of the OFDM. As you can see, this is the frequency spectrum of the signal being transmitted through the channel. Each frequency have a specific amplitude, as you can see on the y-axis, showing the amplitude of the signal being transmitted. One thing to notice here is that in the middle, at the zero frequency, we are not transmitting anything. This is actually standard practice for the Wi-Fi. The last part of the simulation of the FDM is testing the OFDM. Okay, uh, we do that using a parameter called bit error rate, which is basically compares the bits that are sent at the transmission side to the bits that we are receiving. We will do that by also changing the amount of noise the transmitted signal is facing. To do the performance testing, we just adjust the block diagram to include integer to bit converter at both ends, and then we compare. After running the simulation multiple times across different channels, each channel has its own SNR value, we see a very clear trend, a very clear exponential trend, because look at the value of the bit error rate at SNR20. This is 23%. And then look at the SNR at 30. It's almost diminished. These are actually very good results, meaning as long as we secure somewhat of a highly good channel, the technique actually transmits very well. This means that the orthogonal frequency division multiplexing has highly importance in the process of transmission using Wi-Fi.
In conclusion, we learned how Wi-Fi works, explored the key technology like OFDM and QAM, and saw through our simulation that higher SNR lead to the lower BER, confirming that OFDM-based Wi-Fi systems are reliable and efficient for high-speed wireless connectivity. That's all from Group 8. Thank you.